In this project, we studied how our Heron's fountain worked by measuring how high the water went and how long the fountain ran for. After building and testing the setup, we used Bernoulli's equation and the full energy equation to help explain what was happening in the system. These equations allowed us to look over at how pressure, velocity, and energy losses affected the water as it moved throughout the fountain. During the experiment, we collected data such as the nozzle diameter, the amount of water used, the straw dimensions, the pump head, the flow rate, the water temperature, and pressure. This information helped us better yet understand the conditions the fountain was operating under.
The materials we used for this experiment were 3 plastic water bottles, all 16.9 ounces, plastic straws, electrical tape, a hot glue gun, a drill, water, food coloring, ruler, and scissors. We first took 3 water bottles and drilled 2 holes in all 3 bottle caps. Then cut straws into 9, 11, and 15 inches and taped them together. One of the water bottles we cut in half to use for the top piece, and the other bottles we glued together with hot glue. The 11-inch straw ran from the top bottle into the second, the 9-inch straw ran through the bottom 2 bottles, and the 15-inch straw ran through all of the bottles.
It was also necessary to take some measurements before completing the experiment, including the lengths of the 3 straws, which, as specified before, were 9 inches, 11 inches, and 15 inches, and they all had a diameter of 0.1875 inches. The 3 plastic water bottles all had a diameter of 2.375 inches. The height of the entire system was 19.5 inches. The water level of the bottom bottle was 1.125 inches from the ground, and the water level in the middle bottle was 15.5 inches from the ground.
Once all assembled, we added water into the top bottle, allowed the bottom bottle to fill up to the middle straw, and flipped the system over, allowing the water to run into the second bottle. The final step was to add water to the top bottle and watch as the water started pouring out of the top straw.
The first of these is the conservation of energy equation, which explains that as a water particle travels up this system, it will slow down and its kinetic energy will get converted to vertical potential energy. The equation for the conservation of energy is 1/2 mv1 squared equals mgh2. As you can see, there are m variables on each side of this equation, and finding the mass of this control volume can be very difficult, so the equation can be simplified to v1 squared equals 2gh2. After filling in the variables with the measurements we found, we can find that the velocity at the bottom of the system is about 3.1 meters per second. Next is hydrostatic pressure, which explains that the pressure exerted onto water in the bottom bottle depends on the density of the fluid, the gravitational acceleration, and the height of the system. When plugging in our measurements, the hydrostatic pressure of this system is 47.649 kilopascals. Pascal's principle justifies how the force pushing the water into the bottom straw is equal to the pressure forcing the water out of the top straw. And the continuity equation explains that when the cross-sectional area decreases from the water bottle to the straw, there will also be an increase of velocity. And finally, the equation tying all the above equations together is Bernoulli's principle. We just talked about how pressure remains constant throughout the entire system, which means that velocity and vertical potential energy need to work in tandem to keep these two sides of the equation equal. Before closing our video, we wanted to share some takeaways we got from the project. First, we must acknowledge the fact that our Heron's fountain is an imperfect system with imperfect proportions and shape. Different materials and building processes may help minimize room for error and losses. Next, the equations that explain the Heron's fountain do not account for losses due to friction, errors in building, and other factors. Other equations are available to use to account for these losses, but more information may be required to solve them. Finally, the key advice we can give is do not skip preparation. Be sure to research the ideal proportions, materials, and building methods for your fountain's performance. If you're using a 2-liter bottle, you'll likely need tubes with a greater inner diameter than the straws we used in our experiment. Some tools will work better with different materials, and some materials work better together than others.
Daisy, last slide. Overall, based on our data, this experiment showed how small design choices can make a big difference in how a Heron's fountain performs. We saw that nozzle size, water volume, and flow restrictions all influenced the height and duration of the jet more than we expected. Comparing our data to the theoretical models also highlighted how real systems always include losses that equations alone can't perfectly capture. Adjusting friction factors and loss coefficients helped us better match the predictions, reminding us that experiments and models work best when used together. In the end, the project helped us understand fluid behavior in a simple but hands-on way and gave us a clearer picture of how energy, pressure, and design choices interact in real fluid systems.